So welcome again. It's Stephen. This is part two of my thinking about Higgs boson and how its mechanisms of interaction with elementary particles leads to them having mass through two different mechanisms. One which the normal mechanism involving a single particle that gives mass to most of the standard particles, or most of the particles of the standard model of physics of the quarks and the electron and the various gauge particles of the weak force and whatnot. And then this doublet coupling, which is a proposed thing. It's not. I don't know how it would ever be proven, but I think it's the latest thinking on how neutrinos, these ultralight, mysterious, very weakly interacting with matter, so they're very hard to detect because they don't trip detectors. So they're very hard to detect and to quantify. But they're quantum particles. They acquire mass in some way that's thought to be this doublet interaction with two Higgs bosons simultaneously. And it's the most common massive particle in the universe. So there are trillions of them everywhere, every second. That's amazing how many to even think about such a thing that. In a way, the emptiness of space is occupied by neutrinos that are constantly interacting with the Higgs field. So the Higgs particle is a vector particle of the Higgs field, which spreads entirely throughout space, and it's everywhere at all times, ready to donate. Mass in these two ways that we're talking about, to regular standard particles, and then set aside the Higgs particles, or the neutrino particles, which come in a left-handed version only. And one of the problems in physics is that how is it that when matter was created in the beginning, that wasn't created equally as matter and antimatter? Everything appears to be in a quantum state. The creation from a quantum state would appear to direct it towards equal amounts of matter and antimatter, and then as the two substances collide, they annihilate each other, and so the universe should not have anything left in it. But we know that it has more matter than antimatter, and so why is it that is? And then I don't recall why it is that the nature of that is called a left-handed. Something about a way the universe is left-handed causes it to be more matter, and I don't know that it's a coincidence or not that the neutrinos are only left-handed particles, but it probably has to do with the same thing, that the same idea that the left-handedness of the universe has something to do with the left-handedness of the Higgs particle. There's no right-handed Higgs particle, and that's why we require two Higgs bosons to create them. So that's kind of a history, and we were talking a little bit about gravity being, we think of gravity as a warping of space, but I they said, well, it's not really an attractive force. It's not a force. It's a warping of space, and things fall into each other as you go down the hole of the warp. I still like to think of it as an attractor in general. And I like to do that because it seems like you see attractors everywhere. The world it forms, it clumps. The whole universe, the world we live in, life itself, it tends to form clumps of like things. The clumps are the right amount of dispersed and clumped for us to exist. Yeah, so there's this idea of a dark energy that is pushing us apart, but then there's this there's this gravitational clumping, and which one is stronger will ultimately decide whether the universe continues to expand forever or recollapses. I think that right now the thinking is the dark energy way overwhelms the gravity, and so we're destined for an ending of just complete dispersion. But we have the right kind of clumping. We have the right kind of disbursement versus clumping that, to exist. This is the anthropic principle that we live in a universe that could create us, right? So you can kind of start back from the idea that what do we need to have us, and then you can sort of backtrack and make some predictions about the universe itself. So I like that. I like that idea of gravity as somehow to do with this this clumping that we see. Clumping of proteins to form enzymes, and just clumping of gold within rocks to form nuggets of gold. I mean, it's just it's everywhere and obvious that matter is clumping on all different these like fractal levels of life versus geology versus versus the looking at the entire universe. It's all about that, getting that right, getting the attraction of gravity to the repulsive force of the dark energy. Dark energy is just being our universe expanding faster, so we're flying apart. But I think we see the same thing all over the place. There's oceans that want to dissolve everything, and then here are these fish swimming around, and this clumpiness that allows them to exist in the way that they are, and the world is the way it is because of this fine balance, this idea of fine tuning that you hear. But I think you can make a claim, the fine tuning of the clumping versus the dispersion on universal levels, all the way down to enzymatic levels in cells, and I think in geology and every level you can sort of see that. So I like that. I like the that clumping idea, and then the it can only clump under gravity if it has mass, and it has mass through this Higgs mechanism. And then there's these two mechanisms, and one of the mechanisms, the normal mechanism, that's giving quarks and electrons the everyday matter that we are and deal with, that's giving them their mass through this single interaction with giving them this mass, giving them this ability to conform to the geometry of space-time, or you can say to give them the proper amount of gravitation, and then the gravitation to clump properly somehow. But then here's the thing: there's the other one. There's the neutrino, and that's just as important, because without neutrinos acquiring mass, you do not have matter at all. You need neutrinos are involved in the weak interactions. So in the very early universe, there's quarks, and a quark can transform, a down quark can transform to an up quark, which might be necessary for the formation of protons, and it emits an electron neutrino. So without neutrinos, you don't have quarks evolving into their neutrons and protons, and you don't have neutrons and protons forming into nuclei. So you don't have anything. You don't have anything like as we know it. You just have very highly dispersed energy and very highly dispersed particles that aren't able to transform in a way that does the clumping, right? So those two things are both, those two mechanisms are necessary, and I think there's a lot of work being done right now to try to figure out, is this theory about the neutrinos correct this way? And if so, it obviously has a lot to do with this fine-tuning aspect we have in the universe we have now, with the proper amount of clumping and dispersion. because we wouldn't have that without the formation of mass, so that gravity could do its attractive nature, and we wouldn't have the neutrinos, so that the matter could transform in a way that would then form the nuclei and the atoms and everything, the way that we understand the universe now. So there's something there. There's something deep is still hidden, right, in this. So my original thinking on this was, the Higgs acquiring, or the Higgs being is sort of like the particle that makes things acquire mass. This idea of the God particle, they call it, right? So because it gives things mass, and without that you don't have anything. But you also don't have anything without the secondary coupling, or the couplet interaction of the Higgs particles, so that the neutrinos can acquire their mass, and by acquiring their mass, they can work their magic in the transformation of basic quark electron matter into the matter that we see in the universe, that can then, and with that formation of atoms and things, we get the beginning of this clumping. So there's these scalar ideas, and so we have the clumping now finally of atoms forming because of this double way that the Higgs performs. So gravity itself, and attractiveness, I like that better than the warping of space-time. It's this attractiveness principle, and where else do we see that attractiveness principle, and how might it apply? Anyway, that's part 2. I don't think there's going to be a part 3, because we don't know enough to go on, but we have enough to sort of ponder, how that might apply to other things, how that idea of attraction and clumping and dispersion applies to other parts of our lives. Thanks.